Well, good morning or good afternoon, depending on your location. Welcome to the CSG Midwest webinar, Reconductoring the Midwest. Thank you very much to everyone for giving us some of your time on what I hope is a beautiful late spring afternoon or morning in your part of the country. I want to just introduce myself. My name is John Davis. I am the CSG Midwest staff liaison to the Midwestern Legislative Conference's Energy and Environment Committee. The committee is the host of this webinar, which we hope will prove to be informative and thought-provoking. As you can see on the welcome slide here, this webinar is being recorded. The recording will be available to registrants and on our website late next week. If you have a particular request, please go ahead and use my email address there, initial jdavis@csg.org. We just ask, as you are probably all veterans of webinars by now, to please mute your audio during the presentations and feel free to type questions in the chat feature. My colleague Christina Luperini and I will be monitoring the chat for questions to present to our panelists during the points during the presentation, or to save afterwards for Q&A and discussion. Also feel free to use the raise your hand feature, and we'll call on you accordingly. With that, I'd like to turn it over to one of the Energy and Environment Committee co-chairs, Illinois Senator Laura Ellman, who will introduce our speakers. Senator Ellman, take it away.
Thank you, John. I'm really excited for today's webinar. By way of background, the Midwestern Legislative Conference's Energy and Environment Committee is one of 6 MLC standing policy committees. These bipartisan, binational committees get together state and provincial legislators around specific topics of regional interest, including, in addition to our fabulous Energy and Environment Committee, agriculture and rural affairs, criminal justice and public safety, education and workforce development, health and human services, and Midwest-Canada relations. Today's webinar touches on both energy and the environment. It will examine a verb I'm not familiar with, reconductoring, or rewiring existing high-tension electric transmission lines as a way to enhance the Midwest's electricity grid more quickly and at less cost than planning, approving, and building new transmission lines and the myriad energy and environmental benefits that would result. Please note that following our guest presentation this morning or afternoon, depending on your location, we will set aside the remainder of our time for what I hope will be an informative and robust conversation among all participants. So be prepared to jump in with questions, comments, observations, things that you are seeing in your state or province when we open the floor for discussion. So I'm thrilled. I actually had the chance yesterday for just a brief few minutes to meet our speakers today. Our guest speakers today are Casey Baker, who serves as Senior Program Manager at GridLab, and Cassidy Craighill, who serves as GridLab's Technical Education Director. Mr. Baker has spent over a decade in the utility industry working in a variety of roles, including transmission planning, transmission interconnection contract management, which must be really exciting, distributed energy resource planning, and solar PV site management. Before joining GridLab, he managed the energy supply and microgrid program for Liberty Utilities California electric utility. He holds a BS and an MBA in mechanical engineering from the University of Nevada in Reno. Ms. Craighill has spent years advocating for an equitable clean energy transition and engaging audience about the challenges inherent in a 21st century energy system. After earning a master's from Georgetown University and publishing research about public perceptions of complex technologies, Cassidy worked for Greenpeace USA for 7 years. And prior to joining GridLab earlier this year, she was a member of the founding team of Clean Virginia. They're here to walk us through the how and the what of reconductoring and highlight state level policies for us to bear in mind when considering whether to adopt reconductoring in our states. And I'm thrilled. Cassidy, the floor is yours. Welcome.
Thank you so much. We're very excited to be here. And indeed, interconnections I find very interesting, but rest assured, I'm not going to go too wonky with this. I've brought Cassidy with me to pull me back up for air if we get too much into the technical details of any of these things. This is going to be more exciting than maybe my bio might indicate. So I'm going to go ahead and start the show. And give me 1 second to share my screen. Okay.
Looks good to me, Casey.
Looks good. Great. Thank you. All right. And today we're going to talk about advanced reconductoring, but we're also going to set the stage for transmission more generally. Electric transmission might be something that you're aware of in your state. You might have heard inklings about electric transmission and its key role it plays for reliability and resiliency of our nation's energy grid. But I'm going to take a little bit of time to explain why that's so important and why this topic is coming up more and more frequently today. And then I'm going to introduce some new technologies, such as advanced conductors, that can be deployed very rapidly in the next 18 months to 2 years to help increase our transmission capacity, which will provide a variety of benefits, along with clean energy integration, but also resiliency, reliability, and reduction of energy costs. Then I'm going to take a little bit of a moment to talk about the long-term solutions that we can address when we think down the road further from these technologies, and do a little bit about FERC Order 1920, which many of you may have heard of. It was recently adopted by the Federal Energy Regulatory Commission, and even though it's federal regulatory action, there's a huge role for states to play in that order, and I want to touch on that briefly. We're going to have 3 points during this where we'll pause to take questions. So in the meantime, please feel free to add those questions to the chat. And at the bottom of slides, whenever I reference a study, I took the hyperlink for that study and put that at the bottom of the slide. So you will, if you don't already have access to these slides, you will have access to them following this talk. And you can feel free to go to any of these studies and access them and take a deeper dive. Really quickly, so Cassie and I are from GridLab. We're a 501c3 nonprofit. Our role is really providing technical support and education for really technical topics that have to do with the electrical grid. And my background in transmission planning, I focus mostly on transmission. So as you can imagine, I'm really excited to talk to you all today about transmission technologies. To start, I want to take a review of the state of the electric system as it sits today, and in particular in the Midwest. You may not know it, but the Midwest is divided up into many different electric markets and electric regional transmission operating organizations or independent system operators, which is a fancy way of saying that the states have come together, the utilities within these states have come together rather, and developed these systems to cooperatively plan the transmission and generation system in their particular region. And the Midwest is in a unique position, and I've highlighted the states that I believe are represented here. But most of the states and provinces are in a unique position where there's overlapping between these jurisdictions. And you can see in particular overlapping between the Southwest Power Pool, the Mid-Continent ISO or MISO, and then the PJM interconnection. And this creates an interesting dynamic where these utilities are cooperatively planning within their own region. But when it comes to planning from region to region, you get some very interesting outcomes that we're hopeful can be addressed in the near future so that these regions can operate more effectively together. We'll get into that a little bit more later. My background, transmission planning, is a place where it used to be a windowless office where the PhDs would go. And my wife jokes that I was the C3PO. All I did all day was focus on the worst case scenario and think about the worst things that could happen to the grid and develop solutions to prevent those bad outcomes from happening. And that's the perspective that I bring to GridLab. Is reliability is really the number one focus, and from that, we can build a reliable and clean energy grid in the future. However, many of you are aware that the grid is in a bit of a crisis lately. And you can see in particular in the Midwest, the NERC, which is the North American Electric Reliability Corporation, the group that is tasked with identifying these macro level grid threats, has identified the Midwest in particular as having elevated risk of outages. And a lot of this has to do with the extreme weather that we're starting to see, both hot and cold periods that the grid just wasn't designed to handle before. In addition, an issue that I don't think has gotten adequate coverage is the electric reliability's impact on our national defense and national security goals. And I know that this is a macro federal level issue, but when you think about the communities in your state, many of these communities are defense communities. And this Association of Defense Communities has identified the transmission system as a serious threat to both the functionality of the national security complex, as well as the functioning of these defense communities where these defense soldiers and operators actually live and work. And what they point out is that this lack of interregional transmission, which is a fancy word for saying transmission between those regions, when I showed you that map, is really exacerbating the damage of these extreme weather events and really putting both our day-to-day Main Street communities at risk, as well as our national defense communities at risk. When we look at what's causing these outages, the Energy and Information Administration is really showing that it really is these major weather events that's causing these outages. The rate of outages from normal day-to-day grid operations is not really driving a significant increase in outages across the country. However, as you can see from this chart, those major events, those major heat waves, those major windstorms, ice storms, Winter Storm Uri and Elliott are really what's driving these extreme outage conditions. And that's what's really causing concern for grid planners, is if these events are going to be becoming more and more likely, we need to have a grid that can handle that. To dig in further, what is really causing these outages? And FERC, as well as several other organizations, have done deep dives into Winter Storm Uri and Elliott. And what they're finding is that one of the big causes of these outages is failures of the actual generators themselves. And in particular, gas generation. The supply chains for gas generation across the country have not been properly winterized during these winter storms. And that's a threat to the supply chain. It's a threat to the ability for the generators to operate. And it's a threat, as you can imagine, for heating. So those impacts to the electrical grid have knock-on effects. And one of the scariest lines I've read in the last several years of me already being a very anxious person was this FERC report on Winter Storm Elliott, where it said New York, Con Edison in New York had to take emergency actions to preserve their gas supply. And had they not done that, gas heating could have been shut off for months or in all or portions of its territory. So imagine New York State, I know that's not part of your region, but imagine your state facing gas heating outages for months and what that impact could have to your communities and the states that you serve. In addition, MISO, the Mid-Continent Independent System Operator, is seeing a similar pattern where gas failures, both of the generators themselves as well as the supply chains and the wellheads where this natural gas is coming from, are failing at a disproportional rate. And that's what's really triggering this impact and this reliability risk that we're seeing across the country, but in particular the Midwest and places like Texas. Not to belabor the point too much, but looking back at various winter storms across the country, we see that these gas generators are having an outsized impact on the threat to the reliability of the system. So when you factor in the percentage of generation that gas provides, it's actually failing at a higher rate than the amount of gas generation is installed. And the reason I bring this up, not to beat up too much on gas, but I think there is a perception that you can fix reliability with more gas plants. And I think there's a conversation to be had there. But at the same time, I think it's important for legislators to really walk into this with clear eyes and recognize that there is no silver bullet for reliability. And we need to start thinking about this more holistically. The second issue with the grid is economics. And we are starting to see increasing costs for transmission congestion across the US, but again, specifically in the Midwest and the Southwest Power Pool and MISO regions, we're seeing increased what are called congestion costs. What are congestion costs? They're effectively the cost of the transmission system being undersized to deliver power where it needs to go. And what that looks like is you end up turning on more expensive power in places than the low cost places because your transmission system isn't big enough to transfer power where it needs to go. Congestion used to be sort of an afterthought. 10, 15 years ago, it was such a small thought that it really wasn't driving a lot of projects, a lot of transmission development. But what we're starting to see is now we are crossing into the billions of dollars a year. Across the US, it was $20 billion per year of congestion costs last year of our system not being adequately sized to deliver power where it needs to go. Another study into transmission congestion is finding, and take a look and see if you can find your state here. But what this chart is showing is that there's hundreds of millions of dollars being left on the table of inefficiency in the transmission system by not having adequate connections between these various regions. And I know that, you know, there's a desire to view transmission as the domain of FERC and the domain of the federal, you know, the ISO that retains it. But states, we'll get into this a little bit later, but states have a very key role in the development of transmission, and namely siting is one of the main roles that FERC has repeatedly said is the domain of states to handle. So this isn't something to, so this is something to think about. And finally, what I think many of you all are dealing with is economic development or demand growth. For the first time in maybe 20 years, states are starting to see that electric power users are growing and that there's an increased demand for electricity. When you think about our economy of the future, electricity is the bedrock through which this economy needs to be built upon. And that is true of data centers, of AI, as well as electrifying factories and electrifying different industries that historically did not use a significant amount of electricity. Many of these industries are moving to electric modes of doing their work. And what we're seeing is that load forecast, those demand forecasts keep increasing. And in many cases, the transmission planners in these regions are raising the alarm that we need to start building our system bigger and bigger now so that we can address, so that we are not the reason that these factories and data centers can't come to our state, if that makes sense. So there are some states, I won't name names, that are already seeing and having to turn away business because they don't have adequate transmission systems to serve these large industrial customers. Um, in addition, there's been huge amount of manufacturing facilities announced in the last 2 years. And as you can see, the lion's share of these are being developed right in your states. And I think as a state legislator, a question you should ask yourself is, if we do all this work to build this economic development, bring jobs to our state, we cannot let the transmission system be the reason that that falls apart. Okay. And that is really a big reason why we're here today. Finally, we're seeing load growth from a variety of things. I mentioned data centers. That's the chart on the right here. Those AI data centers that are making headlines fit into that hyperscalers group. We're seeing huge growth among that region of, or that area of data center development, as well as EV charging load and the impacts that that has on the grid. And not just full Tesla pure EVs, but also plug-in hybrids are playing a role in starting to impact the grid and how much demand it can serve. The chart on the left here is not a projection. This is a real chart, and you can see that despite many news articles describing EVs not really taking off, you can see it is a parabolic increase of EV adoption in the US. We have reached the milestone of 4 million EVs sold in the US. So these are things to think about when you're thinking about the transmission system. Can my state serve all of this demand that's coming? That's the bad news. And now we're going to transition into the good news, but I do want to take a moment to see if there's any questions about, again, C3PO here warning us about, impending problems that we're seeing. I see one question: is transmission always within a region RTO? How many grids are connected? Great question. In the Midwest, most of the transmission is included in some version of an RTO, whether it's the Southwest Power Pool, MISO. Alberta has its own Providence ISO. There are a few regions that are a little bit outside of that, but I'd say, just to guess, maybe 90+% of your states are covered by an ISO or an RTO. And then we'll get into this a little bit. So there's the jurisdictional map that I showed you. And then from a technical perspective, there's 3 grids in the US. There is the Western interconnection, the Eastern interconnection. They're more or less divided by the Rockies, and there's very little transfer capacity between the two, very little transmission. So you can imagine building transmission across the Rockies, pretty tough. And then there's ERCOT, which is the Texas interconnection, and its own interconnection and very little connections to that outside world. So that's a technical perspective, and then the jurisdictional is where the RTO ISOs come in.
So just to follow up really quick, Casey, so those congestion costs are the inability to move electricity even within a single ISO?
Correct. Yes, okay. Correct. Yeah. Yeah, thank you for that distinction. Those transmission costs are experienced within individual regions. Yeah. And are there any other raised hands? Apologies, I can't see the raised hand. I can see the chat, but.
Not at this time, Casey. I think we're
okay.
I think we're all right to go ahead.
Okay, sounds good. So again, that was the bad news. Here's the good news. Technology in the transmission world has advanced significantly over the last 15 to 20 years, and we're going to talk about how we can use that technology to fix some of these problems. The first is get more out of the system. And you may have heard the term grid enhancing technologies, or GETs. This can be done very quickly, very inexpensively. In many cases, it's just adding a small meter to the equipment so that you can more efficiently run the system we have today. The first example of that is dynamic line ratings. And the way I like to think of it is it's like a dynamic speed limit. So depending on weather conditions, you might have a speed limit go up and down. If it's really rainy, icy, cold, the speed limit will go down. If it's a beautiful, sunny bluebird day, the speed limit might go up. Dynamic line ratings work the same way. If it's a really cold day, you can push more power through the transmission system, and you can adjust how much power you're pushing through it based on the temperature and wind in the system that day. And you can adjust it in real time, down to the 5 to 10 second range. You can be adjusting things up and down to respond to the weather. Most of the grid today, the limit that's placed on the grid today is a static limit, and it may adjust seasonally, but it very much is, this is the line limit. That's how it is under the worst case scenario for that season. Whereas dynamic line ratings give you a little more flexibility so that you can squeeze more energy through the system. The second is power flow controllers, and I like to think of this as like a smart traffic light system. You may not know this, but the transmission system really operates like it follows the energy goes where it needs to go. There's very little control that operators have of the system outside of being able to adjust the generators up and down. Power flow controllers are a new technology. They're based on inverters, or many of them are based on inverters or other electric technology, and they are giving fine-tuning controls to grid operators. As you can imagine, the more fine-tuned controls you have, the more effectively and efficiently you can run the system, and you can start to reduce those congestion costs and get greater value out of the existing system you have today. The third one is topology optimization, and this is a computer machine learning AI exercise, it is a sophisticated software that can identify how you can adjust the grid in real time to more efficiently move power around. So switching transmission lines in and out so that power can go where it needs to go without overloading the system in areas where it might be weak. So a way to think about this would be a detour during road construction. Where can the computer software will look at the system as a whole and adjust the system so that it doesn't overload areas that need to be rebuilt or something like that. So that's the first step. The second step is increase the capacity of the existing system. Within the footprint of our existing system, there are many tools we can use to increase the capacity and reliability and resiliency of the system. The first is fairly straightforward. You can raise the towers. Lines are rated based on how high they are off the ground, because the more power you push through a line, the more it sags. And the more it sags, the more you're at risk of wildfire, the more you're at risk of public safety issues, the more you're at risk of it flashing over and taking the whole line down. So one thing to take away from this presentation is sag is bad. Anything you can do to reduce that sag of the line is going to increase your reliability of the line. It's going to increase how much power you can flow through the line. It's going to reduce wildfire risk and public safety risk. There's new technologies available now to do this. This company here has developed a methodology to actually raise the tower while it's still energized, compared to the old method, which is take the line out completely, use 5-6 cranes to raise each tower. These folks are able to do it while the line is energized and do it safely. They've developed a technology that holds the structure in place while they're able to jack up the line and push more power through it. And they have, I don't have them in front of me, but they have done projects in the MISO and SPP region. So these folks have done work in many of your states. Second way, advanced tower design. There's been a lot of advancements in how we design and build structures over the last 100 years. So when you see these 100-year-old lattice structures that probably line many parts of your state, remind yourself there's new ways to build these structures. And one of those is this bold structure, which can transmit even more power than these traditional lattice structures and also take up a much smaller footprint as well as be shorter. So it's kind of a win-win-win-win there. It's a shorter tower height, it's a smaller footprint, and can transmit more power than the conventional lattice structures. If you can't take the line out of service, there's this exogrid structure, where you can actually increase the throughput of the existing structure by adding a structure on top of it, which sounds a little impactful. I can recognize that. But when you're in a situation where another power line just cannot be built, this could be a solution. And then finally, there's HVDC conversion. There's a lot of talk about this, and many of the Canadian colleagues on this call may be more familiar with HVDC conversion, because HVDC is very useful when you're trying to transmit power a long distance. So if you have resources, let's say hydro resources in parts of Canada, and you want to transmit those into big cities where that energy could be used, HVDC, high voltage direct current, is a technology that's been around for many years, but there's been some breakthroughs in that technology to enable to transmit huge amounts of power. And we're seeing really big results in China and India and Northern Europe. And unfortunately, we're not seeing a huge amount of development on this yet in the US. All right, the big topic of the day, high performance conductors or advanced conductors. What can we actually do if we just replace the wires that are up in the tower? And there's been, through material science breakthroughs over the last 15 to 20 years, they've developed new wires that can double or sometimes even triple the capacity of the existing line just by replacing the wire itself. So not even touching the structures, just replacing the wire. And on top of that, you're reducing your energy losses. So from an energy efficiency perspective, there's benefit there as well. And finally, you can increase resiliency. Remember when I said sag is bad? Many of these conductors have virtually zero sag. So when they heat up, because of the high performance materials being used, they don't sink down when you push power through them. And so you're reducing wildfire risk, you're reducing public safety risk, you're reducing flashover risk and reliability risk. What does it actually look like in the field? Well, you start with an existing power line, and what you do is you actually remove just the wire. In many cases, some to many cases, you may actually have to do some retrofits to the existing structures, depending on how old the structures are. So if these are structures 15, 20 years old, you're probably good with just replacing the wire directly. If these are structures that have been up for 100 years, you might actually have to go in and do some reinforcement or tower raising or foundation repair as needed to repair these structures. However, in most cases, this is still much cheaper and faster than building a whole new power line and acquiring a whole new right-of-way. And then finally, once your structures are ready to go, you can then install high performance or advanced conductors and double or triple the capacity in the same footprint. This is where our study came in. So the question we set out to answer was, if we were to deploy advanced conductors rapidly across the country, what is the benefit that could be seen across the country? And what we found is that a combination of rapidly increasing our advanced conductor use, as well as increasing the rate in which we build new transmission, can save the country about $400 billion by 2050. Why is there savings? Well, going back to that congestion question, when the system is undersized, you are stuck using the generators in your immediate region. And those generators sometimes are not the most cost effective. It's much more cost effective in many cases, in most cases, I would say, to look beyond your immediate area and look for resources in the surrounding area, as long as you have the transmission to access that. The one thing that you could think about transmission is almost like a port in a sense. And I know most of the states here are landlocked, so maybe that's not an apt metaphor. But what transmission is really access to a marketplace. And the more access you have to that marketplace, the more you're going to see reduced costs. And our modeling demonstrated that if we were to pursue both reconductoring with advanced conductors as well as expanding new transmission, there's significant savings being left on the table today. I'm going to pass it now to my colleague, Cassidy, to then say, okay, what does this mean for state legislators?
Great, thank you, Casey. Hey, everybody, I'm Cassidy, coming to you from Charlottesville, Virginia, and Virginia will actually be one of the case studies we talk about, but I'm going to start with Montana, actually, and just walk through two different approaches to legislative intervention, and then talk a little bit about why legislative intervention here is even necessary and what makes utilities unique in this way. So if you want to think about it sort of as a carrot and a stick approach, Montana is a little bit more of the carrot and a really interesting example of how to deploy reconductoring with advanced conductors. So as Casey was mentioning earlier, SAG is bad, particularly for wildfire hazards, and that is a huge issue in Montana. So those conventional steel cables were sagging, creating a fire hazard issue, and actually prompted that utility there, Northwestern Energy, to upgrade a 105-mile line with those advanced conductors. And the Public Service Commissioner in Montana was really a champion on this particular technology. And I have a quote here from him that I'll just read aloud very quickly. In some circumstances, switching to high efficiency power line can cut line losses by a third, and with time, the upgrades can pay for themselves. Better efficiency also makes better use of baseload power generation and reduces the need to purchase energy at peak market prices. So really interesting commissioner perspective there, looking at it holistically. Actually, if you click that link, Casey, that I've put on the slide there, you can see some pictures if it loads of commissioner. Yeah, they're actually installing some of those advanced conductors. I think it's always helpful to sort of see what these things look like in the real world. So that was just one line, and almost like a pilot project. And then, yeah, great, Casey, if you'll stay on this for just a second. So using that pilot project and how successful it was, legislation that spurred legislation in 2023. And the commissioner actually worked with legislators, I believe, on the drafting of it, which coming from Virginia is a little bit unique. So that's an interesting factor there. But the bill that they passed last year, nearly unanimously, it had one dissenting vote in a Senate committee, but then unanimous on the floor, basically provided a financial incentive for utilities to adopt these advanced conductors projects on a wider scale. And what the financial incentive really is allowing utilities to recover through their rate base the upfront costs of this installation if it basically passed some cost effectiveness criteria. So is it decreasing those electrical losses that Casey had mentioned, or are there any other benefits to the consumer and to the overall system, and then obviously the environment as well? So that has been the law of the land in Montana for coming up on a year. It has a project under development now that will then go to the commission for the precise determination of what that, I believe they call it an adder, basically what that return on investment adder might be for a project like this. So moving east, if you'll advance, Casey, to Virginia, where I'm coming to y'all from today, a bill passed this session that is a different way of going about advanced conductors from a legislative point of view. So data center load, as Casey was referencing, huge issue in Virginia. They're all concentrated in Northern Virginia, and massive load growth from that data center expansion. In Virginia, there are integrated resource plans filed every other year by the utilities. Dominion is the largest by far utility in Virginia. It serves about 2 out of 3 customers, with Appalachian Power serving basically the south side of the state, which is much more sparsely populated than Northern Virginia, where a lot of these data centers are going. So this bill, you can go ahead and advance, Casey, that passed this year, HB 862, passed from a Democratic General Assembly and then signed by a Republican governor. I should say that this was a rare diamond in the rough energy bill that passed this year with bipartisan agreement. So pretty huge deal, really difficult to get some energy bills passed this year. But this one seemed a lot like a no-brainer. All it really did was require Virginia utilities to consider not just advanced conductors, but the whole family of grid enhancing technologies in their IRPs. Or, and here's the stick, although I'll admit kind of a mild stick, is to provide justification for the exclusion of those GITs in the IRP. So if Dominion doesn't adopt GITs in their next IRP, they really have to justify why. And this stick is obviously largely dependent on the authority of the regulatory agency in any given state. Dominion Energy didn't oppose the bill, so I think it's really critical to have utility support, obviously, on these bills. Montana was so unique, and it was really almost pioneered by the utility, but it's a little bit different in Virginia. They also just received federal funding for grid modernization efforts that would include this kind of technology, so that can really lighten the load on ratepayers. Yeah, Casey, you can go ahead. Great. So quickly, just to chat about why these types of legislative solutions are even warranted. There are some, just regulatory barriers to being able to get these projects up and running, despite all of their consumer and technical and environmental value. First off, being the high upfront costs. I think Casey touched on this a little bit, but the actual conductor themselves are about double the cost of a traditional one, but you're getting double the capacity. So those high upfront costs can sometimes be a barrier for utilities who are really typically incentivizing major infrastructure projects. So, because they are compensated with a rate of return on those. So these upgrades and improvements can sometimes be less financially attractive, hence Montana's financial incentive being a good case study there. Also an issue with being sometimes intentionally slow to adopt new technologies to avoid those risks on cost recovery. So some of these legislative solutions that I already discussed about, requiring them to consider them in their IRPs is on the table, creating those shared saving mechanisms where utilities and customers share those savings over the long term, really de-risking the technology by providing that rate recovery option is a great way to provide a financial incentive or a business model really for adopting this. Requiring multiple benefit streams to be included in IRP, so really looking at that long-term holistic benefit. And then energy efficiency standards, I think Casey touched on a little bit as well, for transmission lines is a good metric to actually include, like how much are we getting out of these lines. And I think that is all the slides. Yes. Do we want to pause for any questions? I don't think I see any.
Yeah, we could take a brief pause.
I have a question, unless there are others in front of me.
Please go ahead.
So on the reconductoring, installing those higher capacity transmission lines, are there any issues with only doing partial replacements? Like kind of having a high-speed highway, for a segment, and then on both other segments having just your normal 35 miles an hour. Is that, and I'm sure there are, optimal designs for replacement, but is that part of it?
Yeah, that's a great question. And where these technologies actually got their start was exactly that. Just upgrading a small portion of the line where there might be a specific sag problem. So like, let's say it was a span that went over a river or went over a, environmentally sensitive area. They might put this conductor in that one spot to prevent the sagging in that area. The problem you run into, and I like your metaphor of a high-speed freeway, is that unless you upgrade the whole line, you really don't see that capacity benefit. And you could think of it as, if you had a 35-mile-an-hour line, but then or 35-mile-an-hour freeway, and then it opened up to 75 miles an hour and then back down to 35, you're probably going to end up with the same traffic that you would have at some point along that freeway. The same is true with upgrading just a segment of a transmission line. That said, you don't need to upgrade the whole system itself. You do get benefits if you do upgrade one line at a time. And that's what we see most utilities actually do, is they won't try to upgrade all of their lines at once. They'll try to upgrade it one at a time.
Yeah, got it. Interesting. And then do you have data showing the capacity increases? Because, if you require that full for that whole line or for that loop to have that, yeah, is there data showing how that works?
Totally. I would direct you to our report, and
Okay.
it has been put in the
Is there a
chat.
link? Yep. Okay.
And what's included in there is there's several case studies of this technology actually being deployed. There's some utilities that have started using it already without any of these incentives, purely to meet demand load. That's really what's driving a lot of this, is that they just cannot build transmission fast enough to keep up with the demand that's
Yeah.
moving to their state. And so they're deploying this technology to increase that capacity. So there's some great case studies in there. There is one in Minnesota, which is in this region. 3M is one of the manufacturers of these advanced conductors. So they used a 3M product and increased the capacity, as well as, I think the driver for that specific project was that span issue. But as a result of that, they ended up increasing the capacity of the line as well. So it's kind of a cool case study that's, I believe, the intro for for that report that's linked in the chat.
Okay.
And one more question. I presume that the smart grid technology that some utilities may have employed, it's agnostic, the grid are
Yeah,
kind of
that's a great
agnostic to that.
question. Thank you. That is a good question. So advanced conductors, if you can see this is an advanced conductor. It's literally just the wire itself. And so any smart grid technologies that might have been deployed, measurement devices or operational devices, will work with the conductor. Or with the advanced conductors. And in fact, in some cases, it's actually better. So in some of these manufacturers, they put fiber optic cables inside the conductor themselves to verify the health of the conductor. And what we're seeing is that some of these smart grid tools can use that health signal to increase the resiliency even further. So we're really seeing a step change in the grid that my grandfather worked on, that's still up in the air today, to the grid where, smart grid tools, advanced materials are making it much, much more resilient.
Thank you. We do
Thank
have one
you.
other question in the chat.
Oh,
Yeah, it says, when you talk about incentives for utilities beyond federal funding streams, are there other examples of states providing other incentives to give the utilities the liberty to test new technologies?
yeah. I'll hand that off to Cassidy to explain that.
Yeah, good question. So I think going back to the Montana example, I don't think, I think that's a pretty good one of, this is one specific new technology. You can come to the commission, this bill is now allowing the utility to come to the commission and say, we want an ROI, quote unquote, adder, to be able to recover the costs of this advanced recovery, or excuse me, of advanced conductors through our rate base. The other piece to think about too is this could be part of a broader regulatory incentives, like along the lines of performance performance incentive mechanism. So if you had if in your state there's anything like that, you could have a PIM is what they call it, for any kind of technology that, you know, over time saves money, increases the efficiency standards of a line, decreases things like sag and the associated hazards and risks. So I think in terms of just a financial incentive for advanced conductors, Montana is a really good example. But then you could think of this more broadly in terms of incentivizing utilities to do things like this overall, which is where performance-based regulation or PIMs to a lesser degree come into play. Anything else, Casey, you'd want to add there?
Thank you, Cassidy. I know that one other state, New York, was looking at a cost savings shared plan. So if a utility was to install advanced conductors and recognize an energy efficiency gain because you're reducing the losses on that transmission line, the savings from that would be shared between their electric customers as well as the utility itself. And I don't know the specifics of how that was broken down, but that's a way you can incentivize this without having a real dollar, a real cost associated with it, because really what you're doing is you're sharing the savings of that investment over time. And that's another mechanism that you can use that has, somewhat of a revenue neutral approach to it. Okay, I'm going to move forward. And this section I'm going to go through a little quickly because there are folks that have there's going to be a lot of training opportunities on this long-term regional transmission planning. And I've linked some opportunities in this presentation, so you're more than welcome to get into it. But I do want to take a moment to just discuss why are we talking about long-range transmission planning today, and what can state legislators do in the face of that. Going back to, I did describe technically, so the regions have their jurisdictional, so MISO, Southwest Power Pool, PJM, those are planning regions. But in terms of physics, as I mentioned, the Western US, Eastern US, and Texas are not really connected to each other. And this is where we're starting to see a significant amount of reliability impacts, is when these regions aren't connected to each other, we see the impacts much more concentrated in specific areas. And tragically, I think we saw that most acutely in ERCOT in Texas, where despite having significant generator resources, the failure of those resources during Winter Storm Uri resulted in deaths of over 100 folks in Texas. And going back to what I mentioned, an issue that I don't think a lot of folks yet have grasped is that there's serious national defense and national security implications to this. There's an assumption that, military bases have backup generation and they can ride through it. And what we see from our defense community research is that that's not a fair assumption. In many cases, these generators failed as well during Winter Storm Uri. And in many cases, ERCOT had to shut down power service to several of these military installations, and the military installations had to be evacuated during Winter Storm Uri because of this lack of transmission interconnection and the ability to lean on their neighbors. Because during Winter Storm Uri, some of Texas's neighboring states were fine, had excess generation. They weren't suffering these issues. And if the transmission system had the ability to transfer energy between these regions, they could have more successfully ridden out that extreme weather condition. And that's where we get the tagline, we need a system bigger than the weather. So if your transmission system is larger than these extreme weather conditions, you're much more likely to have that resiliency and reliability. I'm gonna skip this, but just say that we're seeing similar issues during Winter Storm Uri and Winter Storm Elliott. I know Texas isn't part of this region, but Southwest Power Pool is. And they too, during these extreme weather conditions, we're seeing significant need to lean on their transmission interties with the other regions to keep the lights on. Going back to the value of transmission between these various regions in the Midwest, in just one in just one winter storm, we're seeing tens of millions of dollars of value in new transmission between these regions. And that value is coming from the ability to keep the lights on, as well as the ability to lean on lower cost generation. As you can imagine, if you're in extreme weather condition and half your generators have gone offline, the remaining generators are going to be much, much more expensive. If you have electric transmission to pull power from other regions that are not as impacted at that time, there's significant value being left on the table here in the tens of millions of dollars. One tagline that we've seen from this, Lawrence Berkeley National Lab has done deep dive studies into this. And what they find is that only about 5% of hours contribute to about 50% of transmission's value. So it's this insurance policy where when you don't have it, you don't really notice it until you need it. And then when you need it, you really, really need it. FERC Order 1920 was developed as a response to these growing grid threats and the recognition that regional transmission planning just isn't happening. And so there's a big role for the federal government to play here because it is interstate, interregional by and large. However, they have carved out a huge part for states to play a role. And that's going to happen both at your state regulator level as well as the legislative level in terms of what powers you want to provide your regulators to participate in these stakeholder processes to do these transmission plans. I'm not going to read through all of this text. So that's why I put this image here of, I mean, FERC Order 1920 is 1,300 pages. So we're just going to very quickly go over this. But what I think is important to hit at is it's a new style of transmission planning. It is zooming out. It's looking at the whole region over the next 20 years, and it's including things like extreme weather and other extreme scenarios, let's say extreme demand growth through artificial intelligence or electrification of manufacturing, and then identifying the benefits of that transmission, and then moving forward to building it. So at its heart, FERC Order 1920 is telling these regions you need to do long-range multi-value transmission planning. And once they develop that plan using the best practices that we have available today, you need to work with your states to gather stakeholder input and to identify who's going to pay for those upgrades. And that is a really important place for where states can play a role in who's going to pay for it and where it's going to be sited. I will say, going back to our near-term solutions, there also is a bit about right sizing, which says that it's encouraging transmission owners to increase the capacity of their existing system when needed and giving transmission owners the opportunity to do that and encouraging that right sizing is the phrase that FERC is using there. Okay, so the order was just filed a few days ago. So the next year is going to be the utilities and the planning regions developing their compliance filing. But part of that compliance filing, they have to open a 6-month engagement period with the relevant state and entities. And that's going to be different depending on which state. And apologies, my Canadian fellows on the call. I know this isn't super relevant to you, but I would imagine as the energy market in the US goes, there's going to be pull on the energy market in Canada. But there is a 6-month engagement period with relevant state entities. So over the next year, you're going to be hearing about these stakeholder processes for FERC Order 1920. And these regions need to propose a method of cost allocation. How are they going to calculate who pays and who benefits from these lines? And those stakeholder process meetings are designed to really gather that information and allow for states to have a role in designing those cost allocation methodologies. There also is an opportunity for a state agreement process. This process is not really used that widely today under FERC Order 1000, but there is an opportunity for states to work together. So this is something you could think of is, hey, our region needs more transmission. Could us 4 states work together and develop a state agreement to bolster transmission in this certain way? Maybe it's building a large HVDC line from one section to another. So there's an opportunity for states to get really involved in this if they so want to. All right, so to bring this to a close, and apologies, we're a little bit long on the presentation. That's my fault. As you could tell, super excited about transmission. But to bring this to a point, states have a large role to play in transmission. I want to dispel the myth that transmission is regulated by the FERC and therefore not part of what states need to be paying attention to. Regulators, when they're evaluating integrated resource plans, the IRPs, they really need to be focused on resiliency. Is your resiliency spend being adequately allocated? Are there lower cost solutions like advanced conductors or grid enhancing technologies that are not being implemented? And if so, why? Do defense communities in your state have adequate representation in the process? In many states, those defense communities, those critical energy users, don't have a role in the IRP process. And could you build a role for them, or have your regulator build a role for them to bolster that? Is interregional transmission considered in utility integrated resource plans? In many integrated resource plans or IRPs, interregional transmission is sort of an afterthought. The thinking is we're just going to build transmission for our state. We're not going to look anywhere out of it, or even smaller, we're going to look just inside of our utility. We're not even looking to other regions of our state. How is that being considered? And empower your regulators to ask those questions. Some states are now going so far as developing their own consolidated transmission plan. Minnesota is one of those that does that. What they do is collect the transmission upgrades being proposed by all of the utilities in their state and developing a biennial transmission projects report. This is more or less an informative report. There's not a lot of follow-on work built upon this, but it is helpful for the state to have a clear-eyed view of how transmission is being developed in their state and where the opportunities might be. Another method is an electric transmission authority. This was created by state legislation in Colorado. And what this group does is actually seek out where to build these new transmission corridors in a way that respects the community of the independent state. So rather than having the utility come in and say, we're going to build a line here, 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 have the state be in the driver's seat of identifying these high value transmission corridors and building those out. These are questions you could ask yourself. Should your state be proactive in establishing transmission corridors, or should you wait for the utilities to propose them? States have a role in developing corridors for everything else, water, traffic, all of these corridors, most of them occur at the state level. Should the state be proactive in trying to develop these transmission corridors in anticipation of this transmission need? And then I've listed the different state committees here where those stakeholder processes in Order 1920 are going to take place for the vast majority of your states is in MISO, SPP, or PJM. Yeah, so with that, I'll open up the floor to questions. Looks like a request for a copy. Yes, my understanding is that everyone should receive a copy of this presentation. I've included my email here as well. I'll put it in the chat. Oop.
All right. Thank you, Casey. And I just want to add that a copy of the presentation will be posted on the CSG Midwest website next week, along with the recording. So if anyone does need or has trouble finding that, or needs any help with getting that, I will, you can also contact me at the address I just posted.
Are there any other questions? I don't think so. Wow, this, in Illinois, where I'm from, we're talking about transmission. But wow, you brought a whole set of layers to it that I wasn't even aware of. So I'm going to start digging into this. This is really interesting. Thank you so much.
Of course.
The grid enhancing technology is also really interesting. And I encourage legislators and from both Canada and here in the United States to look at what, so in Illinois, we have got some rate-based and formula rates that the ICC, our Illinois Commerce Commission, oversees, where utilities will propose things, and then they can get approval or not. So I think that's our mechanism, but I'm going to dive a little bit deeper on that too. Thank you, Casey and Cassidy, and thanks to GridLab for this informative presentation. I'd like to thank everybody who joined us and participated today. And I welcome those in the future who are going to watch this recording because I thought it was great. It will be available on CSG Midwest website, as John said. And with that, hey, I'm going to wish you all a great afternoon. It's afternoon everywhere here now, and a wonderful Father's Day weekend. Thank you so much.
Thank you so much, Senator. This was a pleasure.
Thank you. Thanks. Bye-bye.